The universe is 13.8 billion years old. That number, large as it seems, is written in 11 digits, 13.8 billion. You can say it in a breath. A reasonably patient person can count to 1 billion in about 30 years, 13 of those, and you have the age of the universe. Now, consider this. The last explosion in the universe will occur at approximately 10 to the power of 100 years from now. This is not a typo. It is not an approximation in the order of magnitude sense. It is a number derived from peer-reviewed physics, published in the MON-THLY Notices of the Royal Astronomical Society in 2020, by astrophysicist Matt Kaplan of Illinois State University, who calculated when the universe's last stellar remnants will finally detonate in a kind of supernova that has never yet occurred in the history of the cosmos, and will not begin occurring for a span of time so vast that no human language contains a word for it. 10 to the power of 100. This number has 100 digits. Write it out, and it is 1 followed by 100 zeros. For comparison, the estimated number of atoms in the observable universe is approximately 10 to the power. Explosion in the universe has 100. You could fill the observable universe with atoms, label every single one with a different number, and still not have enough to write the year the last explosion will happen. And, between now and that moment, the universe will not simply sit quietly and wait. It will pass through eras so different from the present that the current state of the cosmos, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, burning through nuclear fuel and lighting the night sky, will eventually look, from a long enough perspective, like a brief and almost inconceivably bright flicker at the very beginning of time. We are living in that flicker. This video is about what comes after. Most descriptions of the universe's future stop after the stars die. Red dwarfs burning out after 10 trillion years. The last star going dark, leaving only cold remnants drifting in an expanding void. End of story, but the story does not end there. After the stars die, the universe enters eras that are not dark in the simple sense of lacking starlight. They are eras with their own physics, their own objects, their own kinds of events, some of them as violent as any supernova, occurring in condition S, so different from anything that exists today that the physics required to describe them has only been worked out in the last few decades. The universe's story is much longer than anyone who stops at the death of stars realizes. And the ending, when it finally comes, is stranger than any ending that has been imagined before the mathematics was worked out. This video is the full biography of the universe, from now to the farthest future that current physics allows us to describe. It is organized around 5 eras, a framework developed by astrophysicists Fred Adams and Gregory Laughlin and introduced in their 1997 paper, expanded in their 1999 book, The 5 Ages of the Universe. Each era is defined by what kinds of objects dominate the universe and what kinds of physics produce its most significant events. The current era, which they call the Stelliferous Era, the star-filled era, will last approximately 100 trillion years. That sounds vast, and is. But it is the first, and in some ways the shortest of the distinct phases the universe will pass through. What follows the Stelliferous Era is the Degenerate Era, the era of stellar remnants, white dwarfs and neutron stars and brown dwarfs drifting in expanding darkness. Then, the Black Hole Era, when even those remnants are gone and only black holes remain. Only evaporating through a quantum process that Stephen Hawking first described in 1974. Then, the Dark Era, after the last black hole has evaporated, when the universe is a diffuse, cold sea of elementary particles moving apart from each other in an expanding void that will never again produce structure. And then, longer after all of that than the entire preceding history, the black dwarf supernova. By the end of this video, you will understand each of these eras precisely enough that the numbers involved, numbers so large that ordinary language has no words for them, will be connected to specific physical processes that make them not just large but meaningful. And you will understand what the most recent science, including a June 2026 paper that definitively settled a recent challenge to the framework's foundational assumption, has changed or confirmed about this picture. What exactly is a cosmological decade, and why do astrophysicists use them to describe the universe's future instead of years? What happens to matter after all the stars die, and why is nothing not the right answer? If a black hole evaporates through Hawking radiation, what does the evaporation actually produce, and what is left when the last black hole is gone? What is a black dwarf supernova, and why is the number 10 to the power of 100 the time at which they begin? And what did a 2025 South Korean paper claim about the universe's expansion? And why did a June 2026 rebuttal in the monthly notices of the Royal Astronomical Society, led by Dr. Phil Weissman and co-authored by Nobel laureates Adam Rees and Brian Schmidt, conclude that the claim was wrong? This is not a video about the heat death of the universe framed as tragedy or cosmic horror. The far future of the universe is not a story of meaningless decay. It is a story of physics continuing to operate, producing objects and events, some of them as dramatic as anything that has happened yet, simply on timescales so long that they sit outside any intuitive human framework for time. The honest version of this story requires honesty about uncertainty. The far future depends on physical laws that we have not yet fully measured, whether protons decay, what dark energy is, and whether it will remain constant, whether quantum gravity produces effects that change Hawking radiation calculations at late times. Each of these uncertainties changes some part of the timeline. Where the science is uncertain, this video says so. Where it is well established, this video explains why. Before we go further, if the idea of a universe biography that spans from now to a number with 100 digits is the kind of story that pulls you in, subscribe to Galaxy Pulse. We go the full distance. Now, back to the 5 eras, starting with the one we are in. To make sense of the universe's long future, we first need a unit of time that does not collapse under the weight of the numbers involved. Because years fail us almost immediately when we try to think at these scales, and even billions of years begin to look like rounding errors by the time we reach the eras that follow the death of stars. Fred Adams and Gregory Laughlin introduced the concept of the cosmological decade in their 1997 paper, and expanded it in their 1999 book. A cosmological decade, written with the Greek letter eta, is defined simply as the exponent of 10 in the age of the universe measured in years. We are currently at cosmological decade 10. Because the universe is approximately 10 to the power of 10 years old, 10 billion years. This notation compresses the incomprehensible into something navigable. Moving from cosmological decade 10 to cosmological decade 11 means going from 10 billion years to 100 billion years, a factor of 10 increase in actual elapsed time. Moving from decade 15 to decade 20 means going from 100 trillion years to 10 quintillion years. The same step size on the logarithmic scale, but representing another factor of 100,000 increase in actual elapsed time. At each step, the universe does not just get older. It enters a genuinely different physical regime. To build some intuition for these scales, it helps to anchor them. The Sun will exhaust its hydrogen fuel in roughly 5 billion years. Cosmological decade 9, 7. The last red dwarf stars will die at roughly cosmological decade 13 to 14, 10 to 100 trillion years from now. That interval, from now to the death of the last star, is about 90 to 100 billion years, which sounds vast, and is, but is still only 1 decade on the cosmological scale. The entire span from the Big Bang to the present is 1 decade. The span from the present to the death of the last star is another decade. And then, the universe has roughly another 32,000 decades still ahead of it. With this tool, the eras become addressable. The Stelliferous Era spans roughly cosmological decades 6 to 14. We are at decade 10, close to the midpoint of the era in which the universe generates most of its energy through nuclear fusion in stars. The current state of the universe is almost inconceivably active. There are approximately 2 trillion galaxies in the observable universe, each containing hundreds of billions of stars. The Milky Way alone contains between 200 and 400 billion stars, and it is producing roughly 1 or 2 new stars per year. Across the entire universe, roughly 1 star forms every second. Most of these stars will not last until the end of the Stelliferous Era. Massive stars, those above roughly 10 solar masses, burn through their fuel in millions of years, producing spectacular supernova at the end and leaving behind neutron stars or black holes. Medium-mass stars like the Sun live for roughly 10 billion years, but there is a third category that will define the long future of the Stelliferous Era: red dwarfs. Red dwarf stars, with masses between about 7 and 50% of the Sun's mass, are far more numerous than Sun-like stars and far more frugal in their fuel consumption. The smallest red dwarfs burn hydrogen so slowly that they will remain on the main sequence C for up to 10 trillion years, or cosmological decade 13. They are misers, as Adams and Laughlin put it, hoarding their fuel while the profligate massive stars have long since exploded. As we move from the current cosmological decade toward decade 14, the universe's population of active stars will shift progressively toward these red dwarfs. Sun-like stars will die and leave white dwarfs. Massive stars will have long since exploded. The universe will grow progressively redder and dimmer, as the remaining stellar population becomes increasingly dominated by faint, red, slow-burning stars. By cosmological decade 13, the last red dwarf stars will be consuming the final reserves of their hydrogen. By decade 14, essentially, all conventional stellar fusion will have ceased. The Stelliferous Era will be over. What the universe will look like at that moment is worth picturing, not darkness, at least not yet, but a fading. The night sky from any planet that still existed would show no bright stars, no blue-white supergiants or yellow sun-like stars, only the dim mist, reddest embers, spread thin across the sky. Each one, the last of its kind. Each one consuming its final hydrogen at a rate slow enough that it will persist for another billion years or more, but no longer bright enough to be called a star by any Jenner-Ouse standard. And then, one by one, they go out. The expected endpoint of the Stelliferous Era, from the perspective of any life that might still exist at that time, would be the gradual dimming and extinction of every star in the observable universe. Not an explosion, not a catastrophe, but an exhaustion. The last star, a small red dwarf somewhere, finally depleting the last of its hydrogen, swelling slightly, and collapsing into a white dwarf. The night sky, from any vantage point with a view of that star, going dark. This image, the death of the last star, is where almost every popular account of the universe's future ends. The stars die, darkness falls, entropy increases, heat death approaches, end of story. The strange part is that this is not even close to the end of the story. At the moment the last star dies, the universe will be approximately 10 trillion years old, 10 to the power of 13. In cosmological decades, the universe will be at about decade 13 or 14. The age of the observable universe at that point will be roughly 1,000 times its current age. And the universe will have roughly cosmological decades 15 through 100 still ahead of it before the last black hole evaporates. That span, from the death of the last star to the evaporation of the last black hole, is itself a span of time that dwarfs the entire preceding history of the universe, by factors that human language has no ready vocabulary for. The Stelliferous Era, all 100 trillion years of it, will look, from the perspective of the black hole era, like a brief opening chapter. The stars dying is not the end of the universe's story, it is the end of chapter 1. The Stelliferous Era ends not simply because stars exhaust their fuel, but because the universe eventually runs out of the raw material to make new ones. Star formation requires cold gas, specifically, molecular hydrogen gas at temperatures cold enough to collapse under its own gravity and initiate nuclear fusion. This cold gas exists today in abundance in the giant molecular clouds that fill the disks of spiral galaxies. Stars form from these clouds. When they die, some of their material is returned to the interstellar medium through stellar winds, planetary nebulae, and supernova. Some is locked away in stellar remnants. Over time, the balance shifts. More material gets locked away in white dwarfs and neutron stars and black holes than is returned to the interstellar medium available for new star formation. The star formation rate, already declining from its peak about 10 billion years ago, continues declining. Galaxy collisions, which can trigger bursts of star formation, become less common as the universe expands and galaxies spread apart. Long before the last red dwarf exhausts its fuel, the rate of new star formation will have dropped to essentially zero. The universe will have entered a state where the stellar population is simply aging, the massive stars already gone, the medium stars turning into white dwarfs one by one, the red dwarfs slowly dimming over hundreds of billions of years. This transition, from active star formation to an aging stellar population with no new additions, is already underway. The star formation rate in the current universe is about 10 times lower than the peak rate, which occurred approximately 10 billion years ago, when the universe was about 3 billion years old. We are already past the universe's peak of stellar activity. The Stelliferous Era is not at its height. We are past its height, living in the long, slowly dimming afternoon of the star-forming universe. The peak was billions of years ago. What we observe around us, the Milky Way, the stars visible in the night sky, the active star-forming regions in nearby galaxies, is the universe well past its most productive era, declining slowly toward the long, dark quiet that follows. Three concepts need to be clear before we move into the post-stellar eras. The first is what a white dwarf actually is and why it matters for the universe's long future. When a star between roughly 0.8 and 8 solar masses exhausts its nuclear fuel, it expels its outer layers as a planetary nebula, and the remaining core, now unsupported by fusion, collapses under gravity. But the collapse stops. It is halted not by fusion but by a quantum mechanical effect. Electron degeneracy pressure. Electrons, as fermions, resist being in the same quantum state. When the core becomes dense ug, this resistance stops the collapse, and the star stabilizes as a white dwarf. A white dwarf is not generating energy through fusion. It is a hot, dense object that radiates away its stored thermal energy over time, cooling slowly, like an ember that is no longer burning but still glowing. Left alone, a white dwarf will cool for trillions of years, eventually becoming a dark, cold, crystalline sphere called a black dwarf. No black dwarfs yet exist, because the universe has not been around long enough for any white dwarf to cool to that state. The second is what dark matter's role will be in the far future. Dark matter is not directly relevant to stellar physics during the Stelliferous Era, because it does not interact with electromagnetic radiation or with the nuclear processes that power stars, but it affects the large-scale structure and the dynamics of galaxies over time. As the universe expands and galaxies spread apart, dark matter halos will remain bound to their galaxies longer than the baryonic matter in the galaxy's disks. Gravitational interactions between stars and dark matter will slowly change stellar orbits, contributing over very long timescales to the dissolution of galactic structure. The third is dark energy, and why it is the most important uncertain variable for the universe's entire future. Dark energy is the name given to whatever is driving the universe's accelerating expansion. It constitutes roughly 68% of the total energy density of the observable universe. If dark energy is truly a cosmological constant, a fixed energy density of empty space, the universe will expand forever, cooling and thinning but never reversing. The 5-era framework assumes this. But decay, the dwarf energy spectroscopic instrument, has been measuring the expansion history of the universe with unprecedented precision, and its 2024 results showed statistical hints that dark energy might not be perfectly constant. The question of whether dark energy is truly constant or dynamical is one of the most actively debated problems in cosmology, and the answer changes the far future significantly. Here is the specific reason why dark energy matters so much for the universe's far future. If dark energy is a true cosmological constant, the universe expands forever. The 5 eras play out as described: stars, remnants, black holes, darkness. The universe approaches heat death asymptotically, always cooling and expanding, forever. If dark energy is instead a dynamical field that grows stronger over time, a different scenario becomes possible: the Big Rip. In this scenario, dark energy eventually becomes strong enough to overcome not just the gravity binding galaxy clusters together, not just the gravity binding individual galaxies together, but eventually the gravity binding solar systems together, then the electromagnetic forces binding molecules and atoms together. The expansion would tear apart all structures successively, from the largest to the smallest, in a sequence ending when the universe literally rips itself apart at the atomic level in a finite time. This would not occur on the trillion-year timescales of the Stelliferous Era. Current models, even those that allow for growing dark energy, typically put the Big Rip more than a few 100 billion years away if it occurs at all. But it would prevent the later eras, the Degenerate Era, the Black Hole Era, the Dark Era, from occurring as described. In November 2025, a team of researchers from Yonsei University in South Korea published a paper claiming, based on supernova analysis, that the universe's expansion was actually decelerating rather than accelerating. This would, if true, represent not just a revision to the far future timeline, but a fundamental conflict with the Nobel Prize-winning observations of 1998. The claim generated substantial attention in the scientific community and popular press. In June 2026, an international team led by Dr. Phil Weissman of the University of Southampton, and including Nobel laureates Adam Rees and Brian Schmidt among its co-authors, published a direct rebuttal in the monthly notices of the Royal Astronomical Society under the title, Still Accelerating. Type Ia supernova cosmology is robust to host galaxy age evolution. The Weissman et al. Team identified two specific errors in the South Korean analysis. The South Korean paper had incorrectly assumed that the AG-E of a host galaxy is equivalent to the age of the progenitor star that exploded within it. These are not the same thing, and had failed to apply the standard host mass correction that modern supernova cosmology requires. With these errors corrected, the South Korean result was fully consistent with the standard picture of continued accelerating expansion. As Rees stated in response, extraordinary claims require especially careful testing. What we find is that when we calibrate these supernova, accounting NG for different host environments and populations, the evidence for cosmic acceleration remains remarkably consistent. The decay 2024 data, showing 2, 5 to 3, 9 sigma hints of dynamical dark energy depending on dataset combination, remains an active area of investigation. 3 sigma result in physics is suggestive, but not definitive. Future decay data releases and independent measurements from the Euclid Space Telescope and Vera Rubin Observatory will progressively sharpen this measurement. The 5-era framework remains the best established picture of the universe's long future. Its foundational assumption of forever accelerating expansion is currently well supported, but the question is being tested. The death of the last star opens the Degenerate Era, and what that era consists of, and what happens in it over timescales that make the Stelliferous Era look like a rounding error, involves physics that is stranger, and in some ways more dramatic, than anything that happened while the stars were burning, white dwarfs cooling, neutron stars slowly losing their rotation energy, brown dwarfs hanging in the dark, galaxies dissolving through gravitational interactions on timescales of 10 to the power of 19 to 20 years. Black holes slowly swallowing any remaining NG mass that drifts within range, and the proton decay question. If protons decay, as some theories of particle physics predict, then all the ordinary matter in the Degenerate Era, every white dwarf, every neutron star, every cold rock and every dispersed atom, will eventually disintegrate into lighter particles and radiation. If protons do not decay, then the matter persists, and the universe's future takes a very different, much longer path. The most exotic event in the universe's future depends entirely on which of these is true. When the last red dwarf star cools below the threshold of active fusion, somewhere around cosmological decade 14, the universe will not be empty. It will be full. It will be full of the remnants of everything that burned and died during the Stelliferous Era. White dwarfs, the cooled cores of medium-mass stars, numbering in the trillions of trillions across what were once galaxies. Neutron stars, the exotic ultra-dense remnants of the most massive supernova, objects roughly 20 kilometers in diameter but more massive than the Sun, where the density is so extreme that matter exists in a state, unlike anything that can be recreated in a laboratory. Black holes, the collapsed cores of the largest stars and the supermassive monsters at the centers of galaxies, objects that spent the entire Stelliferous Era slowly accumulating mass and that will dominate the black hole era. Brown dwarfs, the failed stars that never quite ignited, drifting in the dark having never contributed anything to the Stelliferous Era's light. And planets, billions upon billions of cold, frozen worlds, still orbiting their dead stellar remnants, or drifting alone through intergalactic space, having been gravitationally ejected over long timescales. None of these objects are doing much, by the standards of the Stelliferous Era. White dwarfs have no internal heat source. They are cooling toward the temperature of their surroundings, which is itself falling as the universe expands, and the cosmic microwave background cools. Neutron stars are radiating their rotational and magnetic energy slowly. Black holes are, from the outside, doing essentially nothing until they begin the slow process of Hawking evaporation. But the gravitational dynamics of this crowded, dark universe continue. At cosmological decade 19 to 20, roughly 10 to the power of 20 years from now, something important happens to galaxies. The stellar remnants within galaxies are not in perfectly stable orbits. Over cosmic timescales, gravitational interactions between objects slightly perturb the orbits of everything. Occasionally, two objects come close enough to exchange energy. One is slowed and falls toward the center of the galaxy, the other is accelerated and escapes entirely. This process, called gravitational evaporation, gradually causes galaxies to lose their populations of stellar remnants into intergalactic space, while the remnants that did not escape fall toward the central black holes. By around decade 20, most galaxies will have evaporated in this sense, dispersing their stellar remnants into the surrounding void. What had been the Milky Way will no longer exist as a coherent structure. The Sun's white dwarf remnant, if it still exists and has not been captured by the central black hole, will likely be floating in intergalactic space, cold, crystalline, and alone. One of the most consequential open questions for the Degenerate Era is whether protons are stable on cosmological timescales. Protons are the nuclei of hydrogen atoms. All ordinary matter, everything made of atoms, is made primarily of protons. The question of whether protons can decay into lighter particles, releasing energy in the process, has been one of the most actively pursued questions in particle physics for 50 years. The standard model of particle physics, as currently formulated, predicts that protons are stable, that baryon number, the count of heavy particles like protons and neutrons, is conserved. A proton should, in principle, never decay. But extensions of the standard model, particularly the grand unified theories that attempt to describe the electromagnetic, weak nuclear, and strong nuclear forces as aspects of a single underlying force, typically predict proton decay, with a half-life of somewhere between 10 to the power of 31 and 10 to the power of 36 years, depending on the specific theory. The experimental situation is that proton decay has never been observed. The best current lower limit on the proton lifetime, from experiments like Supernova in Japan, is approximately 10 to the power of 34 years for the most commonly predicted decay mode. This does not rule out proton decay. It means that if protons decay, they do so with a half-life longer than 10 to the power of 34 years. The Hyper-Kamiokande experiment, currently under construction in Japan and scheduled to begin operations in 2027, will have a fiducial volume roughly 8 times larger than Super-Kamiokande, and is expected to push the sensitivity to proton lifetime up to around 10 to the power of 35 years. If proton decay occurs at rates predicted by the most promising grand unified theories, Hyper-Kamiokande could detect it within a decade of operations. Why does this matter for the far future? If protons decay with a half-life of around 10 to the power of 36 years, then by cosmological decade 37, essentially all the ordinary matter in the universe, all the white dwarfs, all the neutron stars, all the cold planets, all the dispersed atoms, will have decayed. The universe will have been entirely converted from ordinary matter into lighter particles, primarily electrons, positrons, neutrinos, and photons. No atoms, no matter in the conventional sense. No white dwarfs waiting to become black dwarfs, just a thin, dispersed sea of fundamental particles in an expanding, increasingly cold space. If protons do not decay, the matter persists. The white dwarfs continue to exist. They cool further, eventually reaching temperatures below a single degree above absolute zero, solidifying into cold crystalline spheres. They become black dwarfs. And black dwarfs have a future that is extraordinary, though it takes an extraordinary amount of time to arrive. Current experimental evidence does not tell us which of these futures is correct. The universe will take one of two very different paths in the Degenerate Era, depending on a physical question that the most sensitive particle physics experiments of the current era have not yet been able to answer. Assuming proton decay does not occur, and black holes remain after the Degenerate Era, we arrive eventually at the black hole era. By cosmological decade 38, essentially everything in the universe except black holes has either fallen into black holes or is a cold stellar remnant slowly being accreted. What dominates is a population of black holes ranging from stellar mass objects, from the collapsed cores of massive stars in the Stelliferous Era, to supermassive objects that were already millions or billions of solar masses at the centers of galaxies, and have spent cosmological decades accreting the occasional remnant that dry F-TED within range. These black holes are not permanent. In 1974, Stephen Hawking published a calculation showing that black holes are not entirely black. Quantum mechanical effects near the event horizon cause black holes to emit thermal radiation, a process now called Hawking radiation. The mechanism involves the quantum uncertainty of empty space. Near the event horizon, virtual particle-antiparticle pairs briefly appear. Occasionally, one member of such a pair falls through the event horizon while the other escapes, carrying energy away from the black hole. The black hole loses mass. Over time, the black hole shrinks and eventually evaporates entirely. To understand why this is a quantum mechanical effect and not a classical one, it helps to think about what virtual particle pairs actually means. Quantum mechanics allows, for brief moments, fluctuations in energy that would be forbidden by classical physics. Pairs of particles briefly popping into existence and then annihilating, borrowing energy from the vacuum and repaying it fast enough that the laws of physics are not violated on average. Normally, these pairs appear and disappear too quickly to produce any observable effect. Near a black hole's event horizon, however, the intense gravitational field can supply enough energy to make one of the pair real. And, if that particle happens to be on the outside of the horizon while its partner falls in, the outside particle escapes as real radiation. The energy to create this real particle comes from the black hole's mass, which decreases accordingly. The evaporation timescale depends on the mass of the black hole. Small black holes evaporate quickly. Stellar mass black holes take approximately 10 to the power of 67 years to evaporate. Supermassive black holes at the centers of galaxies, with masses of billions of solar masses, take approximately 10 to the power of 96 to 100 years to evaporate. These numbers define the end of the black hole era. Somewhere around cosmological decades 98 to 100, the last and most massive black holes in the universe will complete their evaporation. The final moments of a black hole's evaporation are among the most exotic events in all of physics. As a black hole loses mass, its temperature rises. The Hawking temperature of a black hole is inversely proportional to its mass, meaning lighter black holes are hotter. A stellar mass black hole has a Hawking temperature close to absolute zero, far colder than the cosmic microwave background. which is why stellar mass black holes currently absorb more radiation from the cosmic background than they emit as Hawking radiation, and actually grow slightly rather than shrink in the current universe. Only as the universe expands and the cosmic microwave background cools below the Hawking temperatures of stellar mass black holes will evaporation begin to dominate. As the last black holes evaporate, they grow hotter and hotter, eventually releasing a final burst of energy in the last moments of evaporation. A flash that is the most energetic event that will occur in the late universe. The question of what exactly a black hole emits as it evaporates, whether the emitted Hawking radiation contains information about what fell in, is the black hole information paradox, one of the deepest unsolved problems in theoretical physics. Its resolution is important for the long-term story of the universe, because it determines whether the late universe, after all black holes have evaporated, contains a record of everything that ever existed, or whether that information has been permanently lost. Beyond cosmological decade 100, after the last black hole has evaporated, the universe enters what Adams and Laughlin call the dark era. In the dark era, if protons have decayed, the universe is a diffuse sea of electrons, positrons, photons and neutrinos, moving apart from each other in the expanding void. The temperature is extraordinarily close to absolute zero. The density is extraordinarily low, no structures form, no events occur in any meaningful sense. The universe simply continues to expand and cool, approaching heat death asymptotically. This would be the end of the story if protons do decay. But if protons are stable, then the white dwarfs that formed during the Stelliferous Era, those that were not consumed by central black holes during the long gravitational evaporation of galaxies, persist into the post-black hole epoch as black dwarfs. See old, crystalline, dark objects drifting alone in an expanding universe. And, in 2020, astrophysicist Matt Kaplan published his paper in the monthly notices of the Royal Astronomical Society, showing that these black dwarfs will eventually explode. The mechanism is pycnonuclear fusion, sometimes called quantum tunneling fusion. At extremely high pressures and extremely low temperatures, nuclear fusion can occur not through thermal motion, which requires heat, but through quantum tunneling. The mechanical phenomenon by which particles pass through energy barriers that classical physics would prevent them from crossing. In the crystalline interiors of black dwarfs, pycnonuclear reactions very slowly convert lighter elements into heavier ones, gradually building up an iron core at the center of each black dwarf over timescales so long that ordinary language has no purchase on them. To understand why this is possible, it helps to think about what normally drives nuclear fusion. In a star, fusion occurs because the stellar interior is hot, millions of degrees, and the atomic nuclei are moving so fast that when they collide, they occasionally have enough kinetic energy to overcome the electrostatic repulsion between their positive charges and fuse. This is thermal fusion, driven by heat. Without heat, thermal fusion stops, but quantum mechanics offers a different pathway. Even at zero temperature, particles are not perfectly at rest. Quantum mechanics forbids it, through the Heisenberg uncertainty principle. More importantly, a particle approaching a potential energy barrier does not simply stop at the barrier if it lacks the classical energy to cross it. There is a small probability that the particle will tunnel through the barrier and appear on the other side, without ever having had enough energy to cross it classically. This is quantum tunneling, and it is a real and measured phenomenon. It is responsible for radioactive alpha decay and for nuclear reactions in white dwarfs at the edges of stellar populations. In a black dwarf, this tunneling operates at the crystal lattice level. The nuclei in the crystalline interior are fixed in a lattice structure, and the tunnel probability for any given pair of nuclei to fuse is astronomically small at any given moment. T over timescales of 10 to the power of hundreds of years, even astronomically small probabilities add up. Slowly, carbon and oxygen nuclei tunnel and fuse, building heavier elements. Eventually, the heavier elements themselves fuse. Iron-56, the most stable nucleus, accumulates in the core because no further fusion can release energy from iron. The iron core grows. When the iron core grows large enough, it reaches the Chandrasekhar limit, the mass above which electron degeneracy pressure can no longer prevent collapse. The black dwarf collapses and explodes in a supernova. The first black dwarf supernova will begin at approximately 10 to the power of 100 years from now. Not all black dwarfs will reach this point. Only those with initial masses above roughly 1.2 solar masses, the most massive ones that can build iron core ease quickly enough on this timescale, will explode. Kaplan estimates that approximately 1% of all the stars currently in the observable universe, roughly 10 to the power of 21 stars, will eventually produce black dwarfs that explode in this way. The last of these explosions will occur at approximately 10 to the power of 32,000 years. After that, there is nothing left to explode. No more supernova. No more events of any kind, in any sense that matters to physics. The universe asymptotically approaches heat death. The black dwarf supernova are not just the last explosions in the universe. They are, in a specific technical sense, the last things that will ever happen. Before moving to the climax and close in part 2, one more reflection on scale is warranted, because even with cosmological decades as a tool, the later eras resist intuitive grasp in a way that is worth addressing directly. There is a common experience of reading about large numbers in science, 1 billion years, 1 trillion years, 1 quadrillion years, and finding that after a certain point, all the numbers feel equally large and equally meaningless. They are all unimaginably long. This is a natural cognitive limitation. Human intuition about time was shaped by lifespans and seasons and generations, not by the timescales on which quantum tunneling converts carbon to iron in crystalline stellar remnants. The cosmological decade framework does not solve this problem, but it does something useful. It provides a consistent unit that lets you measure the relative sizes of these eras against each other, which is more tractable than their absolute sizes. The Stelliferous Era spans about 8 cosmological decades. The black hole era spans about 60 cosmological decades. The interval from the last black hole to the first black dwarf supernova spans, if protons do not decay, roughly cosmological decades 100 to 100. These ratios are comprehensible even when the absolute numbers are not. The black hole era is about 7 times longer than the Stelliferous era. The wait from the last black hole to the first black dwarf supernova is roughly 1,000 times longer than the black hole era. In this sense, the last supernova in the universe is not just a very far in the future. It is the culmination of a sequence in which each era is vastly longer than the last, and the final interval is by far the longest of all. The universe does not rush to its ending. It extends the quiet, cold, dark period between the evaporation of the last black hole and the explosion of the first black dwarf to a duration that makes everything that came before it look brief. This is the correct way to hold these timescales in mind, not as absolute numbers, but as a sequence in which each chapter is longer than the one before it by factors that grow faster than intuition allows. culminating in a final event that takes longer to arrive than all the preceding events combined. Let's come back to where we started. We live at cosmological decade 10, close to the midpoint of the Stelliferous Era, in a universe that has already passed its peak of stellar activity and is slowly, over hundreds of billions of years, beginning the long dimming that will end with the death of the last red dwarf. After that death, the Degenerate Era, the Black Hole Era, the Dark Era, and finally the Black Dwarf Supernova, each separated from the last by spans of time that make the Stelliferous Era itself look like an instant. The 5 eras are not speculation. They are the output of applying known physics, nuclear physics, quantum mechanics, general relativity, thermodynamics, to the known contents of the universe over long timescales. Where the physics is well established, T timeline is well established. Where the physics is uncertain, as with proton decay and dark energy, the timeline branches, and the branches lead to different endings. The number 10 to the power of 100, is not a guess. It is a calculation, published in a peer-reviewed journal, using known physics applied to the known structure of white dwarf stars, under the known laws of quantum tunneling. It is as well established as any number in astrophysics that describes a future event. It is simply larger than any number that most people have ever been asked to think about. To appreciate what this means, it helps to think about what 100 digits actually implies. Write out the number 1 followed by 80 zeros, and you have the estimated number of atoms in the observable universe. Write out 1 followed by 100 zeros, and you have the year the first black dwarf supernova will begin. The number of atoms in the observable universe is not sufficient to count the digits in the year of the last explosion, let alone the year itself. This is not a failure of imagination. It is a proper y of numbers that grow as fast as exponentials, and it is a consequence of physical processes, quantum tunneling in crystalline iron cores, that are real but extraordinarily slow. Popular accounts of the universe's long future fall into a surprisingly consistent pattern of truncation and omission. The most common version stops at the death of the last star. The stars die, the universe goes dark, heat death approaches. This is technically accurate for the end of the Stelliferous Era, but leaves out the 3 subsequent eras entirely, each of which ns timescales longer than the Stelliferous Era, by factors that dwarf human comprehension. The Stelliferous Era, all 100 trillion years of it, is the brief opening chapter of a book whose final pages extend to numbers with thousands of digits. Stopping the story at the death of the last star is like stopping a novel at the end of the first chapter. A second common failure is treating the 5-era framework as settled while ignoring the most significant recent uncertainty. The decay 2024 data on dark energy. The decay collaboration's 2024 Baryon acoustic oscillation measurements showed statistical hints that dark energy might not be a cosmological constant, with significance ranging from 2.5 to 3.9 sigma, depending on the dataset combination. This is not a confirmed result. A 3 sigma result in physics is suggestive but not definitive. And the June 2026 rebuttal, led by Weissman and co., authored by Rees and Schmidt, reconfirmed that accelerating expansion remains the best explanation for current data. But the question of whether dark energy is truly constant, which is the foundational assumption of the entire E5 era framework, is an active area of research rather than a settled one. Popular accounts almost never mention this tension. A third failure is the omission of the black dwarf supernova result. Matt Kaplan's 2020 paper is one of the most striking results in the cosmological future literature of the past decade. It identified a class of event, the last supernova in the universe, that occurs at times so far in the future that the number of digits in the year exceeds the number of atoms in the observable universe. It received modest coverage when published in August 2020 and has been largely absent from popular science accounts S/C. The result is not merely a curiosity, it changes the picture of the universe's ending in a fundamental way. The universe does not simply fade to black after the last black hole evaporates. If protons are stable, there is a further chapter, vastly longer than all the preceding chapters combined, in which isolated black dwarfs build iron cores through quantum tunneling and eventually explode. The universe has one more round of fireworks left, beginning 10 to the power of 100 years from now and lasting until 10 to the power of 32,000 years. A fourth failure is treating these timescales as if they are merely very long versions of familiar time. A cosmological decade is not simply a long time in the sense that 1,000 years is a long time. The progression from decade 10 to decade 100 involve the universe changing qualitatively, in ways that make each successive era physically different in kind from the previous one. At cosmological decade 10, the dominant physics is nuclear fusion in stellar interiors. At cosmological decade 40, the dominant physics is Hawking radiation from black holes. At cosmological decade 100, the dominant physics is quantum tunneling in crystalline iron cores at temperatures near absolute Z. These are not the same universe at different ages, any more than a caterpillar and a butterfly are the same creature at different stages of the same process. Each era has its own physics, its own characteristic objects, its own kinds of events. And finally, popular accounts almost never address what the framework implies about our current position in cosmic history. We are not at the end of time, we are not near the end of time. We are at cosmological decade 10, the midpoint of the first era. YCH is itself the shortest of the five. The universe is young. Its long future is almost entirely ahead of it. A civilization that forms in the Degenerate Era and manages to survive to the Black Hole Era would look back on the Stelliferous Era as a distant, almost mythological age. The time when the universe was bright, when stars existed, when the universe was doing its most energetic and visible work. That mythology would describe our current moment as the peak of cosmic activity, the brief window when everything was happening at once by the standards of what comes after. The most consequential recent development for the universe's long future is the ongoing debate about dark energy. In April 2024, the Dark Energy Spectroscopic Instrument Collaboration released its first-year Baryon acoustic oscillation results, using the distribution of galaxies across cosmic time as a ruler to measure the expansion history of the universe. The DACY results, when combined with cosmic microwave background data and Type Ia supernova data, showed statistical preference for a dark energy equation of state that changes over time, inconsistent with a simple cosmological constant, at significance levels ranging from 2.5 to 3.9 sigma, depending on which supernova dataset was included. This did not confirm that dark energy is dynamical. A 3 sigma result in physics is suggestive but not definitive, and there are several possible systematic effects in the data that could produce a spurious preference for dynamical dark energy. In November 2025, a team at Yonsei University in South Korea, led by researchers including Young-wook Lee and Junhyuk Sun, published a paper claiming that the universe's expansion was actually decelerating rather than accelerating. The claim was based on an analysis of supernova brightness measurements that, they argued, had been contaminated by a bias in how the ages of stellar progenitors were estimated. If correct, This would represent not just a revision to the far future timeline, but a fundamental conflict with the Nobel Prize-winning observations of 1998. In June 2026, an international team led by Dr. Phil Weissman of the University of Southampton, with co-authors including Nobel laureates Adam Rees and Brian Schmidt, published Still Accelerating, Type Ia Supernova Cosmology is Robust to Host Galaxy Age Evolution in the monthly notices of the Royal Astronomical Society. The Weissman et al. Team identified two specific errors in the South Korean analysis. First, the South Korean paper had incorrectly assumed that the age of a host galaxy is equivalent to He age of the progenitor star that exploded within it. These are related, but not the same thing. And the distinction matters for how stellar population age corrections are applied. Second, the South Korean paper had failed to apply the standard host mass correction that is a routine part of modern supernova cosmology. With these errors corrected, the South Korean result was fully consistent with the standard picture of continued accelerating expansion, as Weissman's team stated. The previous and well-accepted measurements were, in fact, fine, and our current understanding of the fate of the universe remains robust, as Rees added. Extraordinary claims require especially careful testing. What we find is that when we calibrate these supernova, accounting for different host environments and populations, the evidence for cosmic acceleration remains remarkably consistent. The South Korean team has since submitted a counter-rebuttal, which is under review at the time of this writing. The scientific exchange continues. The current state of the dark energy question, as of mid-2026, is that accelerating expansion remains the best supported interpretation of the data, while the decay 2024 hints of dynamical dark energy remain a topic of active research rather than a settled question. Future decay data releases and other surveys, including the Rubin Observatory and the Euclid Space Telescope, will progressively sharpen this measurement. The most significant near-term development for understanding the universe's far future is not a new telescope. It is the resolution of the proton decay question. The Hyper-Kamiokande experiment in Japan, scheduled to begin operations in 2027, will have a fiducial volume roughly 8 times larger than its predecessor, Super-Kamiokande. If proton decay occurs at rates predicted by the most promising grand, unified theories, Hyper-Kamiokande could detect it within a decade of operations. This would not just be a fundamental discovery in particle physics, it would be a measurement of the universe's long-term future, determining whether the path goes through the Degenerate Era, followed by proton decay at cosmological decade 37, or extends to the much longer timeline of black dwarf supernova, beginning at 10 to the power of 100 years. These two paths are not minor variations on the same story. They are qualitatively different futures. On the proton decay path, all ordinary matter eventually disintegrates into a diffuse sea of fundamental particles, and the last events in the universe are the final Hawking evaporation, flashes of the last black holes at cosmological decade 100 or so. On the no-proton decay path, cold black dwarfs persist long after the black holes are gone, slowly accumulating iron cores, eventually exploding one by one in the last supernova the universe will ever produce. The question of which path is correct is, at its core, a question about the symmetries of particle physics, and Hyper-Kamiokande is the instrument best positioned to answer it. The decay experiment will release further data over its 5-year program, refining the measurement of dark energy's evolution with progressively higher statistical power. The Euclid Space Telescope, which began science operations in 2024, will measure the distribution of galaxies across much of the visible sky, providing an independent measurement of the expansion history. Together, these will either confirm that dark energy is a constant, closing the question for practical purposes, or will show dynamica L behavior with enough significance to require a genuine revision of the far future picture. The Laser Interferometer Space Antenna, LISA, a planned space-based gravitational wave observatory, will be sensitive to the gravitational waves produced by merging supermassive black holes. Detecting them will provide new information about the population of massive black holes that will ultimately dominate the black hole era. Understanding the mass distribution of these objects better refines the timeline for when the last supermassive black hole will complete its Hawking evaporation. And the Hawking radiation question itself, the information paradox, may find theoretical resolution through ongoing work in quantum gravity. Several approaches, including holographic descriptions of quantum gravity and the island formula approach to black K-hole entropy, have made significant recent progress toward understanding how information is preserved in Hawking radiation. If these approaches lead to a complete theory, it would resolve the deepest uncertainty in the black hole era's physics. What exactly the universe looks like when the last black hole completes its evaporation, and whether the information about everything that ever fell in is preserved or lost. Here is the most important thing that the far future of the universe shows us about the present. We are not at an ordinary moment in cosmic history. We are at a very specific, and, in the context of the universe's full biography, extremely brief moment. The Stelliferous Era, when the universe happens to be full of stars, and when those stars happen to produce the conditions, warmth, light, chemical complexity, that allow biology to exist. The Stelliferous Era lasts roughly from cosmological decade 6 to cosmological decade 14. It occupies 8 cosmological decades. The full history of the universe, from the Big Bang to the last black dwarf supernova, spans roughly cosmological decades 0 to 32,000. The Stelliferous Era represents 8 out of 32,000 cosmological decades of history, roughly 1/4% of the universe's full duration. We are in the brief, bright window when stars exist. This is not a trivial observation. The Stelliferous Era is the only era in the universe's history when the kinds of chemistry that allow life, at least life as we understand it, are possible. Stars produce the heavy elements through nucleosynthesis. The carbon in your body was forged in the cores of ancient stars that exploded before the sun formed. The oxygen was fused in dying massive stars. The iron in your blood was made in supernova explosions. Every heavy atom in your body is a product of stellar physics, the very physics that defines the Stelliferous Era. None of these elements were produced in any significant quantity before the first stars formed, and after the last stars die, no mechanism will produce them in any quantity again. The Stelliferous Era is not just when the universe is bright, it is when the universe is chemically complex in a way that biology depends on. The energy from stars drives planetary atmospheres. The warmth of stars maintains liquid water on planetary surfaces. The ultraviolet light from young stars drives the chemistry of prebiotic molecules. The neutrinos from supernova explosions may have played a role in the synthesis of the heavy elements that ended up in planetary crusts. Every part of the physical environment that life on Earth depends on traces back, in some way, to the Stelliferous Era's central feature: stars. The universe's far future, the trillions of years of the Degenerate Era, the vastly longer black hole era, the incomprehensibly longer dark era, and the final, occasional black dwarf supernova, All of these post-stellar eras are eras in which the conditions for life as we know it do not exist. The universe will persist for an almost incomprehensible duration in states that are, from a biological perspective, completely sterile. There is no energy source available for metabolism, no liquid water, no chemical gradients to exploit, no stellar warmth to keep anything unfrozen. The post-stellar universe is not hostile to life in the sense of being actively destructive. It is sterile in the sense of being devoid of the conditions that life requires to exist. We happen to exist in the window when it is not sterile. That window is not closing imminently. The Stelliferous Era has roughly 90 billion years remaining before the last red dwarfs go out, assuming our best current understanding is correct. On human timescales, that is effectively forever. Red dwarf stars in the distant future might host habitable planets warmed by their faint light. Some models suggest that low-mass red dwarfs could, in principle, maintain liquid water on nearby planets for trillions of years, opening the possibility that the long tail of the Stelliferous Era, after sun-like stars are gone, might still support the conditions for biology in some environments. The window is longer than it appears from our current vantage point near a sun-like star. But on the timescale of the universe's full biography, we are alive in its brief, brilliant youth. The stars are temporary, the universe is not, and the universe after the stars is longer, stranger, and more mathematically elaborate than any version of the story that ends when the lights go out. 10 to the power of 100 years from now, a black dwarf will explode. It will be, in the most precise technical sense, the last event that will ever happen, and nobody will be there to see it. That is not a tragedy. It is physics, continuing to do what physics does, in the dark, for as long as there is anything left for physics to work with. There is one more thread in this story. The framework of the 5 eras assumes that the laws of physics as we currently understand them remain the laws of physics across all of these timescales. In particular, it assumes that the speed of light is constant, that quantum mechanics remains valid, that the fundamental constants of nature do not change over cosmic time. But there are theoretical reasons to wonder whether the constants of nature, the values of things like the fine structure constant, the gravitational constant, the masses of elementary particles, might not be perfectly constant across all of time and space. Some theories of dark energy predict slow changes in these constants over cosmic timescales. If the fundamental constants drift even slightly over trillions of years, the entire 5-era picture may require revision. Whether the constants of nature are truly constant is one of the most fundamental questions in physics, and experiments are actively searching for evidence of their variation. The answer would change not just the far future of the universe, but our understanding of what physical law itself means. That is a story for another time. We started with a number, 10 to the power of 100. A number with 100 digits, representing the year the universe's last explosion will begin. A number so large that writing it out would require more digits than there are atoms in the observable universe. Then we followed the path that leads there. Through the remaining 90 billion years of the Stelliferous Era, as the last red dwarfs slowly exhaust their fuel, each one a small, dim, reddish star, burning through its hydrogen reserves at a rate so miserable, why it will outlast thousands of sun-like stars. Through the Degenerate Era, with its white dwarfs cooling toward absolute zero over timescales of 10 to the power of 20 years, and the open question of whether proton decay will erase them before they can become black dwarfs. Through the Black Hole Era, the longest of the named eras, as the last black holes evaporate through Hawking radiation over cosmological decades 38 to 100. Through the Dark Era, a sea of fundamental particles expanding in an increasing cold void. And finally, if protons do not decay to the black dwarfs, cold, crystalline spheres, the final remnants of the universe's stellar history, slowly accumulating iron cores through quantum tunneling, one by one, crossing the threshold and exploding in the last supernova the universe will ever produce. We also saw the most important current uncertainties. The decay 2024 data suggesting dark energy might not be perfectly constant. The November 2025 South Korean paper claiming cosmic deceleration, and the June 2026 rebuttal, led by Weissman and co., authored by Rees and Schmidt, which identified two specific errors in the South Korean analysis, and reconfirmed that accelerating expansion remains the best supported interpretation of the data. And we saw the experimental program that will determine the two most important unknowns, hyperchemiok and, which will probe proton decay with 10 times the sensitivity of its predecessor starting in 2027, and the ongoing surveys that will sharpen the dark energy measurement. The universe's biography is not finished, but enough of it is known that we can read most of the first act, understand the structure of the second and third and fourth, and calculate, not guess, calculate, when the last line will be written. Whether protons decay is experimentally unknown, bounded below about 10 to the power of 34 years by current experiments, with hyperchemiok, and expected to push this boundary to around 10 to the power of 35 years. The answer determines whether the universe takes the shorter path through proton decay at decade 37, in which all ordinary matter converts to a thin sea of fundamental particles, and the last events are the final Hawking evaporation flashes of the last black holes, or the much longer path to black dwarf supernova at 10 to the power of 100 years. These are not small differences. They represent fundamentally different physical fates for all the matter that was ever in stars. Whether dark energy is a true cosmological constant or a dynamical field that changes over time is the most consequential open question for the long-term expansion history of the universe. If dark energy remains constant, the universe expands forever, thinning and cooling, and the five-era picture plays out. If dark energy grows over time, a big rip is possible, terminating the universe's story before most of the five eras have a chance to occur. The decay 2024 results showed hints of dynamical dark energy AT2 5 to 3 9 sigma significance. The June 2026 Weissman et al. Paper confirmed that cosmic acceleration is real and current measurements are reliable, but it did not resolve the question of what dark energy physically is or whether it changes over time. The question requires further data. The black hole information paradox. What exactly is emitted in Hawking radiation, and whether it preserves information about what fell in, remains unsolved. Though theoretical progress has been significant in recent years, the island formula approach, YCH, uses insights from holographic quantum gravity, suggests that information is preserved in Hawking radiation in a subtle way that was not apparent in Hawking's original calculation. If this approach is correct, the universe, after all black holes evaporate, is not entirely information-free. It contains, in the correlations among the emitted Hawking radiation, a complete record of everything that ever fell into every black hole. But this resolution is not yet rigorous, and the information paradox remains one of the most contested problems in theoretical physics. Whether the fundamental constants of nature are exactly constant or drift slowly over cosmic time is an open question in physics, with active experimental searches for variation in the fine structure, constant, and other quantities across cosmic distances and d timescales. The 5-era framework assumes constant physics throughout. If constants drift, the timescales for each era change, and the mechanism of nuclear fusion that drives black dwarf supernova operates differently. And the nature of dark energy itself, what it is physically, whether it is a property of empty space, a dynamic field permeating the universe, or something arising from modifications of general relativity, remains completely unknown despite dark energy being the dominant component of the universe's current energy density. Until this question is answered, the universe's far future contains a foundational uncertainty that no amount of careful calculation can resolve. There is a question that sits underneath the 5-era framework and is rarely asked directly. What does it mean to do science about events that will never be observed, and that cannot affect any living thing, at timescales so vast that even the concept of waiting for them is incoherent? The standard answer is that science describes reality, and reality includes the far future, whether or not anyone is there to observe it. The laws of physics do not require observers. Quantum tunneling will happen in crystalline iron cores, whether or not and why civilization persists to watch it. The black dwarf supernova will occur whether or not any mind exists to receive the light. The calculation that predicts them is as valid as any calculation in physics, but there is another way to think about it. The far future of the universe is not just a topic for calculation, it is a context that changes how the present looks. Knowing that the universe is young, that the Stelliferous Era is a brief, bright window, that the conditions for life are temporary features of the universe's current physics rather than permanent features of reality. This changes what it means to exist now, not in a way that produces any particular emotional response, but in the sense that context always changes meaning. A sentence read with full knowledge of the novel it belongs to means something different from the same sentence read in isolation. The 5-era framework is the full novel. We are in the first chapter, everything else is still ahead. First, the universe has a biography vastly longer than its current age. We are at cosmological decade 10. The last event in the universe occurs somewhere around cosmological decade 32,000 or beyond. We are in the opening pages of a very long book, and the book, after the chapter we are in, consists almost entirely of eras without stars, without galaxies, and eventually without ordinary matter. The universe we live in, with its trillions of galaxies and its billions of years of stellar history, is the brief prologue to a much longer story told in the dark. Second, the 5-era framework is physics, not speculation. Each era is defined by the dominant objects and energy sources at that time, and the transitions between eras are consequences of known physical processes. The vast timescales are large because physical processes involved are slow, not because the physics is uncertain. Quantum tunneling in crystalline iron at zero temperature is a real process governed by well-understood quantum mechanics. It just operates on timescales that have 100 digits. The calculation is as rigorous as any in astrophysics. The uncertainty is not in the physics, but in whether the conditions for that physics to operate, specifically, whether protons remain stable long enough for black dwarfs to form, will be met. Third, the most consequential unknowns for the universe's long future are particle physics questions that current and near-future experiments are actively probing. Whether protons decay and whether dark energy is constant are the two most important variables, and both are being measured now. The answer to the proton decay question is not merely of theoretical interest. It determines whether the universe ends its active phase at cosmological decade 37 or continues for another 31,963 cosmological decades beyond that. Hyper Kamiokande, beginning operations in 2027, is the most likely instrument to resolve this question within the lifetimes of people alive today. Fourth, we live in a cosmologically unique moment. The Stelliferous Era, the only era in the universe's history when the conditions for life as we understand it exist. This window is roughly 1/4% of the universe's total duration. The significance of this is not that life is rare or special in some metaphysical sense. It is simply that the physical conditions that life requires, specifically stars and their warmth and chi-Michael products, are a feature of only the current era. The post-stellar universe is not hostile to life. It is indifferent to life in the most complete possible sense. There is nothing in it for life to use. We exist in the brief window when the universe appends to be doing the kind of physics that biology can exploit. Fifth, the last explosion in the universe is a supernova. The same physical process, the collapse of an iron core exceeding the Chandrasekhar limit, that has been producing the most energetic explosions in the Stelliferous Era will, at 10 to the power of 100 years, produce one final flash of light in a universe that has been dark for longer than the entire preceding history of time. The universe ends its active phase, if it ends, with an explosion, not a fade. The black dwarf supernova are the last punctuation mark in the universe's biography. Not a period, but an exclamation point, occurring in silence, witnessed by no one. In a darkness that has persisted for longer than human language has words for. The five-era framework describes a universe whose far future is dominated by eras with no stars, no galaxies, no planets, and eventually no ordinary matter. Given that all human experience and all life as we know it exists in the Stelliferous Era, what does it mean to say this is our universe, when our era occupies such a tiny fraction of its duration? The Stelliferous Era is not the universe in the sense of being its dominant or defining period. It is more like the first few pages of a very long document. Most of the document is written in the dark, in physics that no organism has ever witnessed and none ever will. Whether the universe after the Stelliferous Era is still ours, in any meaningful sense, is a question about what ownership of a universe means. And the answer probably depends on whether anything we create or do during this brief era persists, in any form, into the long darkness that follows. The number 10 to the power of 100 is impossible to intuit. What does it mean to do science about events at timescales where no human, or any descendant of humanity, could possibly be present to observe them? Is this physics, or is it mathematics? And is the distinction meaningful? The calculation that produces 10 to the power of 100 uses physical laws verified in laboratories on Earth and in observations of the universe at its current age. Those laws make a prediction about what will happen to black dwarfs over enormous timescales. If the laws are correct and hold unchanged for that long, the prediction will prove accurate. Whether anyone is there to verify it is irrelevant to whether it is a prediction of physics or of mathematics. It is a prediction of physics applied to a future state of reality. The fact that it cannot be observed from the inside of the Stelliferous Era does not change its status as a physical prediction any more than the inability of anyone in 600 to observe Neptune's discovery in 1846 changed the status of Newton's laws as physical laws. And the most personal question, looking at the five-era framework, knowing that we are in the brief, bright, star-filled window of the universe's history, does that change how you think about this moment? Not in a dramatic sense, but in the specific sense of knowing that the conditions that allow life to exist are temporary features of the current epoch, and that the universe will persist, dark and cold, for durations that make the entire history of life on Earth look like a rounding error. The answer to this question is probably different for every person who thinks about it carefully, but the question itself is worth holding. We are in the first paragraph of a very long story. We are the universe, briefly, observing itself and calculating its own future. That the future we calculate is mostly dark does not make the present moment, or our ability to calculate it, less remarkable. If this one stayed with you, let us know which era was the hardest to hold in your mind. The death of the last star, which is the end most people imagine, but only the first transition. The black hole era, with Hawking evaporation over cosmological decades 38 to 100. The black dwarf supernova at 10 to the power of 100 years, the last events that will ever occur, or the most recent scientific development. The Jun E. 26, Weissman et al. Paper, confirming that accelerating expansion holds, while the Dacey dark energy question remains open. And, if you want more of this, the largest questions in science, told with both the numbers and the uncertainty intact, subscribe to Galaxy Pulse. We will see you in the next one. At cosmological decade 10, a species on a small planet orbiting a medium star at the edge of an ordinary galaxy looked up at the night sky. They counted the stars. They calculated when the last one would die. They calculated what would come after the last one died, and they found that after the last star, the universe continues, for longer than the entire history of stars, until a cold dark remnant, long forgotten, explodes in the silence, and then there is nothing left to explode. And the universe, having lasted for a number with 32,000 digits of years, finally runs out of things to do. We are in the first paragraph. Everything else is still ahead.